All right, so now what I want to talk about, since we already differentiated between sound and hearing, I want to talk about sound specifically, because sound is our wave that we're looking at in this topic. Sound waves are created by vibrating or oscillating objects. You can think about the speaker example that we already talked about in the notes. You could think about a guitar string would be another example of something that's oscillating. Anything that's oscillating and vibrating back and forth is going to create some sound. You might have noticed sometimes lights buzz, or you might see something that is shaking really, really quickly and vibrating, and it gives off a buzz. Anything that has that oscillation back and forth is going to give off a sound wave. When we talk about the mediums for a sound wave, air is the most common medium. Because sound is a mechanical wave, it needs a medium in order to travel. So if you have, for example, trying to make a sound in outer space, you would never hear the sound because there's no medium to pick it up. Sound is a mechanical wave that's pushing through. But air is not the only medium that you can use for sound. If you go underwater, for example, you would still hear the sound coming through, right? So fluids, whether they're liquids or gases, still both can carry sound, but also solids can carry sound as well. If you ever put your ear up to like a table or to a door or to the floor, you can hear the waves that are coming across the door or the floor or whatever you're putting your ear up to still carrying sound. So when we talk about sound waves, we're going to look at it in this class as if it's pretty much just air, but really any medium can carry sound. The last thing I want to talk about sound, besides them needing a medium because they're a mechanical wave, is that they're longitudinal waves. This means that the direction of displacement of their particles, the amplitude, is going to be parallel to the direction of the wave. And I have a diagram in your notes, and you can see it here on the page, where we have shown different areas of longitudinal waves. And each one of these little specks is a air particle. And you can see that some of them are compressed together, and this is the bunching of all the black dots. And then some of them are spread apart. This is the rarefaction part of it, where they're spread out. So you have areas that are compressed, you have areas that are not compressed, and you end up getting this oscillating compression, rarefaction, that is determining what the frequency and the period of this sound wave are. When we talk about hearing against our eardrum, it's these compressions and rarefactions as they're hitting our eardrums that are pulling it back and forth that are making us hear. Another thing I want to talk about with sound, we're going to focus in on this class primarily just looking at sound as it's traveling through air. And since the medium of any wave is what determines the speed the wave travels through that medium, we're going to focus on the speed of sound in air at 331 meters per second. Now, the temperature and the pressure of the air do affect the speed of the sound. However, we're just going to be looking at, in this class, standard temperature and pressure. So we're going to identify just STP as 331 meters per second. As temperature or pressure varies, the speed of sound in air will vary a little bit up or down, but it'll always be right around 331 meters per second, and this is the only thing you need to use. This information is also in your reference tables. So if you look on the front page of your reference tables, underneath the physical constants, you'll find speed of sound in air. It's the fourth item down, 331 meters per second. So whenever we do any calculations that have to do with sound, we're going to use that 331 in order to set it equal and use our wave equation, velocity equals frequency times wavelength. Another interesting thing about sound that I want to talk about has to do with lightning strikes. This is always something that occurred to me and that I always really like thinking about. If you've ever noticed that sometimes a strike of lightning and the sound of the thunder doesn't always happen simultaneously. In fact, because light travels at the speed of light, which is 30 million meters per second, and sound only goes at 331 meters per second, any light flash pretty much happens instantaneously. However, the sound, because it's moving a lot slower, takes a little bit of time to get there. If you ever want to know how far away from a lightning strike you are, you just need to count the seconds between when you see the flash and when you hear the thunder. Every 5 seconds is approximately 1 mile. And that's because after traveling for 5 seconds, the speed of sound in air after 5 seconds moves about 1 mile in distance. So you're always able to tell pretty much how far away you are from a lightning strike by counting the seconds. In this next slide, you're going to go and you're going to start looking at some examples of this. And I want you to try those examples that I'm going to show you in this next slide. And then you're going to try some of these other examples in your Microsoft Forms as I check to see how well you're using this 331 meters per second in order to apply it to the wave equation, velocity equals frequency times wavelength.